sure it works. Yay, there it goes. All right, so we are looking at gravitational potential energy in general. So the idea is about how the mg delta H thing that we know and love from grade 11 and reviewed recently just doesn't work over large distances, because the g value of 9.8 is only really the g value, the acceleration due to gravity, near the Earth's surface. So we have to be able to deal with the fact that changes, and this is what that looks like. Yeah, that's for the answer. Let's make sure I'm doing the right lesson first here. I have a bunch of lessons open, of course. Anyways, yeah, so we're saying this thing is only useful for small delta H's relative to the radius of the Earth. For larger values, the g value changes, gets smaller, and so Eg equals mgh is no longer valid. So what do we do, right? I think they say something like, more than a couple hundred kilometers, and you gotta start dealing with the reality of the situation rather than pretending it's g value is constant. So you get away with pretty big lifts. Anyways, I forget what the exact number is where you have to start to. We could look at the numbers and see like when it starts to actually change, right? But so for larger delta H values, we need an equation for gravitational potential energy that is not just mgh. It's going to be based on the universal gravitational constant. And I'm just going to show you the equation for now. And this is this very similar equation to what you've seen before with the electric force of attraction between, or repulsion between, two charges, kqq over r squared. We have gravitational force is gmm over r squared, so they're extremely similar. And then the resulting energy equations are also very similar. gmm over r now instead of r squared, just like it was kqq over r instead of over r squared. Okay. So this page kind of talks about the idea of where it comes from, but the issue is, of course, that we remember that the force displaced area under the force displacement graph gives the work done, right? So if we had a constant force over a distance or displacement, then you get work done. The issue with gravity, as I've mentioned, is that the force of gravity reduces, right? Based on inverse square law, since it's over r squared. So we have a graph for the gravitational force as you go farther and farther away, curving, reducing, right? So to get that area is kind of tricky. And so the actual process for getting that area involves a calculus process of, the integrals of the adding up all the little rectangles. Some people call it geometric average, but the reality is you're doing that process I mentioned yesterday briefly about the idea of, like, if I split the difference there and make a rectangle, and split the difference there and make a rectangle, and split the difference here and make a rectangle, roughly speaking, we could say, oh, we can add up and get the area, right? Equals the rectangles added up. And then the idea is this size here. If we look at the width of that rectangle, we talk about like delta r, let's call it, as delta r gets really, really small, the area approaches the correct value. Okay, so area approaches actual work done. Basically, the equation, it would give you the equation value of the gmm over r. So, that's a little bit mysterious, of course, right? When you see calculus later on, it's going to make more sense. You can see how that r squared just becomes an r. But, it's not actually as simple as what I'm showing here, but it certainly helps you remember the result. And the idea is simply that, work equals force times distance. And we've got like the gravitational force times r, like the distance you go is r. And that's your gravitational energy, right? So the idea is gmm over r squared times r. So r squared becomes an r. The r's cancel out, right? So it gives that formula in not exactly a true way, but it helps you remember it. The actual true way is calculus, which of course you don't have yet. The high school calculus doesn't even actually cover this anymore. It used to cover integrals, but they've combined and changed the courses, and so you end up doing some algebra stuff in there, so there isn't time to do integral calculus, which is the adding up of areas. So the calculus you do in grade 12 now in high school is all about the slopes. So it's called differential calculus, all about the rates of change and the slopes, whereas the integral calculus is left to university, I guess. Anyways, so we're going to talk about this value of this gravitational energy shortly. Okay, it's going to be considered a negative value, which we are already familiar with from electric energy, from electric potential energy, I should say. So, anyways, basically giving the equation, justifying that it actually exists for real based on calculus, but you know, we can sort of see the idea, like this seems like it proves it, but it's not actually a proof because that would assume constant forces. It just works out conveniently the same. So the idea of the negative energy, we need to make a note of that, right? We're actually going to have on the equation sheet over here somewhere. On the equation sheet, we're going to have, did I put it on this one yet? I don't think I did actually, or did I? So I don't know. I've got some other stuff on there already, so I was kind of thinking maybe I had already put it on there, but I better add it on. We are going to say, I guess it would make sense to do it here. We're going to say EG equals negative right here. Okay. And paste. So this is gravitational potential energy in general. So instead of the mg delta h, if you have large delta h values, you have to consider actual distances that you go, right? This is for large delta h. That's pretty quick here, I think. For large delta h. Right. Do I need to define the variables there? We know what g and m are. Like this is, I think it's fine, right? And so, yeah, that's gravitational potential energy in general. And then we're also going to look at the idea that delta Eg, let's do this, delta Eg will, of course, just equal Eg final minus Eg initial. So I don't even think I need to do the subscripts there. I think it's pretty obvious. Yeah. So that's what we're going to have added to the equation sheet. And I'll just go back to the actual lesson. We're not totally just developing it in anyways, right? So, so the negative idea, I'm just going to get back to that, of course. So as we talked about before, the idea of this is if you're lifting an object away from Earth, so picture this being Earth, make it blue, instead a little more. So we got Earth, and we've got a mass. Right, so Earth is, of course, big M, and the mass is little m. So as we are lifting it away from Earth, right, this is positive work done, positive work. We're looking at like a positive delta E, whatever, right, to get to really far away. And so the idea that the issue is here is that at an infinite distance, right, you end up with 0 joules. So it's 0 joules of energy eventually once you lift it really far away. And at an infinite distance, you've got no gravitational force. Fg equals 0. Well, actually, that's justifying y, I should say. right? So that's considered zero joules of energy there because you're going to have no gravitational force. If you have no gravitational force, that means that the object doesn't have any potential energy relative to that object that would sometimes have forces on it, right? If you let go, it's not going to go anywhere. It's not going to accelerate to the left or the right. It's going to be zero force. And so basically the idea is if we're adding energy to get to zero, then we must have had some negative EG value, right? So some negative number, right, plus something that eventually gets you to zero. So if it was negative 1,000, you add 1,000, you get to zero. That shows that we have a negative 1,000 energy at the original location, right? So about an infinite distance, the gravitational force goes to zero. And so there is zero gravitational potential energy. If you brought the object to that spot and let it go, it actually wouldn't fall back to the earth. It doesn't have potential energy relative to it, right? So right now you lift something to the top shelf and it has energy relative to your foot, right? But if you lift it far enough, it won't actually fall back. So it actually doesn't have potential energy relative to your foot. So that's the exact same analysis and that we talked about previously. This is what I was going for in the recent assignment. I didn't end up holding people to that, or holding it, because I guess I didn't maybe ask the question clearly enough. But assignment 3, electricity and magnetism standard model. And so the question that was about justify the sign of the value here. The one that it's like terms of magnet. Is this the right one? Somewhere along here I had questions about the sign, but maybe it was assignment 2.
I think it was the second assignment.
There we go.
Yeah, I think so too.
And all blending together for me here. Assignment 2. What's nearby? All right. So justify and explain the sign of the potential energy of the system, right? A lot of people just said, well, you've got, opposite charges, so it ends up being negative. And that doesn't really justify why it's a negative energy, right? That just sort of helps you remember that it's a negative energy, I guess, more so, right? It's just a mathematical thing. The actual justification for why, like capital WHY, is this, right? So I have to think about how I can word this question better so that I make it clear what I'm looking for without telling you the answer, right? It's hard, right? So I'd have to say like justify based on the energy that you'd have. I don't know. It's really hard to word it. So you get what I'm trying to say though. Like you probably recognize like, oh yeah, I can see that you're looking for that in that question. Really based on the wording I had there, justify and explain the sign. I'll have to add in like why it is really considered positive or negative or something like that based on analysis of energies near and far or something like that. Anyways, so the idea is, as I've already concluded, if we're adding energy to bring it to a total of 0, we must be adding to a negative value. And so we end up with that general equation that Eg equals negative GMM over R. Okay, as I've added to the equation sheet. So let's, this is just the same graph as we've seen before too, right? The idea of the gravitational potential energy being like a potential well, they call it. So you're stuck down here in the well. In order to get out of the well, in order to escape from Earth, you got to like climb out of the well. You have to add a bunch of energy. So think of how the numbers would work here. This number down here would be actually like a large negative number, right? But it's considered the smaller EG value, but in actuality, it's a larger negative number. So it's hard on the human brain to analyze this because this is a large negative value, meaning it's a small EG value. This one up here is actually of course the larger EG value because we're higher up, right? But it's larger in the way that it's a smaller negative number. So picture a -10 becoming a -7 as you add 3 to it, right? So we're adding 3 to it, getting closer to 0 as a result, right? So it's a little weird, and there's that EG equals final minus initial, of course, like I mentioned. So if you look at the numbers here, we'd have that final of -7, take away that initial of -10, giving us that add of 3. So let me just make that visible for everybody. And I think that's an important page for you to make note of, right? The idea of this value down here is actually going to be like a larger looking number, but because it's a negative number, that means a smaller gravitational potential energy value. So -1,000,000 is a smaller value than -700,000. So I'm kind of hoping you're gonna like jot down the ideas of that, right? Because it is weird. That a bigger negative number means this, right? It means a smaller gravitational potential energy value. Does anybody want that page a little bit more?
I think we're okay. I don't know about everyone else.
Okay. Someone else pick up if they are. Just as long as I get someone saying, yeah, I think it's fine, because it's hard for me to picture what's happening on your end, right? I can't watch you like I do in class. I can't observe and base my judgment, my speed on that. So here's an example of using things here. We've got a 5 kilogram object getting lifted 200 kilometers up. I might have misspoke before, like it's a couple kilometers kind of thing, right, for a lift. If you get to like 200 kilometers, you're gonna have to like deal with the changes, of course, right? I was thinking of that at the time. I was like, wait, that's too far. 200 kilometers is lots. Like you're getting it into near orbit there. So yeah, if we're looking at the amount of work that was done, the idea is, of course, that we're like adding energy, right, to this thing. So we're gonna get like a positive result. We have to think of that, and expect that answer. We're lifting this thing. We've done a bunch of positive work. So that we're just gonna look at the ideas here so we don't get bogged down with numbers. And the ideas are pretty simple. The final gravitational potential energy minus the initial gravitational potential energy. So we're looking at a GMM over, like a negative GM over R, take away another negative GMM over R, right? This final position needs to be like the radius of the Earth plus this 200 kilometers, right? So, and this is just analyzing the idea of the values of these things. So let me come back to that actually. That's what my order of the numbers is there. So there's like the radius of the Earth plus the 200 kilometers. This one's just the radius of the Earth, right? So as a result here, because I'm dividing by a bigger number, you can tell it's going to be a smaller negative number, right? But this is where we have to sort of get our head around the idea of this. I'll say this one here actually. This one's going to be this larger negative number, right? This larger negative number. As we said on the previous page over here, that larger negative number means a smaller EG value. It's just weird. But you can tell that we are looking at, in the end here, gotta get control of my screen again. There we go. Let me get rid of that little thing. So basically here, because we have, maybe I'll do one more line in between here. So we've got a small negative number. So this is negative small. And then see how this becomes add. Looks like a happy face almost. So adding this large number, you can tell we're going to get a positive answer. Okay, so it just makes sense. So what did I have here? I forget. Pen.
Sorry, what does RE stand for?
Radius of the Earth.
Okay.
So the radius of the Earth is that 6.38 times 10 to the 6.
Okay, thanks.
Problem. I'll make a note of that. So this is radius of the Earth. And that's because up here it's like, you know, it's moved from a distance here. So what you want to be picturing is you want to be picturing, I don't know if I've ever enough room here, but we have the Earth itself, right? And so we've got the initial distance between the centers. If an object's there, then they are initially this far apart, RE, right? And then you're lifting it up 200 kilometers. So plus 200 kilometers. So they end up at a new position of RE plus 200 kilometers, that is. I'd have to be careful with my numbers there because this RE value, of course, is that 5.6 point, sorry. I always get those ones mixed up a little bit. 6.38. But again, you just look these up on page 774, I think it is, right? 6.38 times 10 to the 6 meters. Anyways, so, but I didn't want to have this page be a whole bunch of calculations. I want it to be very logical and you can see what you're expecting. Then when you go and fire in a bunch of numbers, there's the actual numbers, right? You get a number in the end, and it certainly better be a positive value, right? We knew going into this that we better be getting a positive answer in there. I'm going to go with purple so it stands out. Yeah, we're going to have this, you know, this better be a positive answer. And that's what it works out to be. It's just a case of firing a bunch of numbers into your calculator. So we get that it was 9.4 times 10 to the 6 joules of work done, positive energy. Okay, so of course it's just get good at using your calculator and your memory button on your calculator and so on, and it's just a case of punching some buttons. What? Oh yeah, what would the old school, you know, just EG equals mg delta h have given us? Well, it would have been mg delta h, so it would have been mass times 9.8 times the 200,000 meters. And so it would give us 9.8 times 10 to the 6. The answer we had seems kind of close, right? It's 9.4 times 10 to the 6, but you have to recognize that's off by 400,000 joules, right? So this number's bigger by 400,000 joules because it's assuming the gravitational field strength is going to stay the same the whole time, whereas in actuality it gets weaker. So you only have 9.4 times 10 to the 6 instead of 9.8 times 10 to the 6. Okay. So you can see that, like I said earlier, there the distance that that this actually becomes an issue up here. Earlier in the video, the recording this, I think I said like up to 200 kilometers, but it's way less than that. Like up to a couple of kilometers, maybe you'd say instead, right? In the example we're clearly working out here, you can see at 200 kilometers, you're off by 400,000 joules. That's a lot, right? It's a lot. So like if you're calculating how much energy for a rocket and so on to end up in the right spot, you're going to be off by a lot if you're off by 400,000 joules. It's not going to work. So that's the questions to do with that. Answers are all worked out, can be posted. And yeah, any questions about that one? So just a new equation to plug numbers into and apply the idea of, just make sure to look at the idea of the final minus initial. It's on this page here, right? So, yeah, it works. The numbers are just annoying, kind of weird, the whole negative idea. So that is new topic number 1, fairly quick and easy. Just have to work your way through it. So should be some time for that. A little extra. I think we've done a little bit early, maybe. So before this is the second one, of course, of our 2 lesson per day quadmester organization. So we're looking at Hooke's law, it's called officially, and that's basically what happens when you are storing energy in springs and getting forces from springs by compressing them or stretching them. And then we're going to look at the energy stored in systems like that as well as part of it. Okay, so to start out with, Hooke's law is named after Robert Hooke, I think his name was, and there's a video that has a little bit more of the history of it. I'll show you in a second. But Hooke's law, it was discovered, it was found that the amount of deformation, compression or stretch, in other words, so we could add that in, deformation meaning a compression or a stretch. That is a compression or stretch. X or delta X, however you want to write it, doesn't matter. It means the same thing. And we're just saying we can use it either way, right? Is proportional to the amount of force required. So if we know the deformation is proportional to the force required, then we know that. That's what we're saying. That's what was discovered. It was discovered that the force is proportional to the amount of deformation, amount of compression or stretch. So that makes it really easy to get an equation, because then you're like, oh, so if they're proportional, then if the division of them gives you a constant value. This constant value is your constant of proportionality, right? It's really like I've said before, it's a property of the system. In this case, it's the property of the stiffness of the spring. Right? Stiffer springs require more force per meter of compression, or usually it's per centimeter of compression. Okay, so basically that gives us a constant K value, and so our Hooke's law is F equals Kx. So F equals Kx. The X is the amount of deformation, stretch or compression. The K is the stiffness of the spring. It's the spring force constant I should add in there. So K equals officially the spring force constant. Just doubling my language there. Yeah, spring of a force constant of, in one of the questions, so it's your spring force constant, just kind of a weird way of describing it. And of course the force. Okay. So I think I could grab this part here and add it to the equation sheet. If I didn't already somewhere, I may have added something. That's this stuff. So I'm going to move that down. That's tomorrow's stuff. There we go. So Hooke's law, F equals Kx. So just a new equation for us to be able to work with. If you, I had a way more at this. I pared this page down to the point where it was sort of just easier to follow. The original page talked a lot about the idea of like how you discover this. I'll mention that briefly enough here. But where does this come from? Well, it just comes from an experimental result, an experimental observation, where you push on the spring and you measure the forces and you see what kind of a value you get. So there is a video there that we can watch briefly just to help you visualize what the heck we're talking about. Cool. I'll skip a little bit through it, but it's okay. It's an all right video.
Hooke's law states that the extension of an elastic material is directly proportional to the applied force producing the extension, providing the elastic limit is not exceeded.
So the part I didn't mention yet was the elastic limit. And so basically you can stretch like a spring or an elastic band or whatever, and eventually you get to the point where it's kind of not really behaving the same way. So I'll mention that when they get to that in the graph and the picture of it and so on.
What does this actually mean? Simply put, Hooke's law basically tells us how far an elastic material will stretch depending on the tension or force applied to it. It is a common law used in physics and engineering. Have you ever wanted to go bungee jumping? How reassured would you feel that the rope attached to your feet would not stretch too far, causing you to hit the ground at 100 kilometers per hour? After the cord passes the point of free fall, it acts as a spring and so falls under the rules of Hooke's law. Through Hooke's law, designers are able to calculate the length the rope will stretch based on the weight of the person attached to it, so that the elastic stops stretching before reaching the ground. Hooke's law is named after Robert Hooke, a 17th century.
There you go, Robert Hooke, 1635 to 1703. I couldn't remember the dates. That's all, but quite a while ago.
British physicist who first stated this law in 1660. So how can we set out to prove this law ourselves? We will now set out to prove Hooke's law by experimentation.
So this is where I'll
on a
skip a
spring
little
and
bit,
its length when
but
different.
basically
We
you're going to
expect our
stretch
result to
springs
apparatus that you will need
various
to spring
distances and record
apparatus that
values,
you will need in support stand, any forces
and they show a
applied,
table of
and again,
values
take
eventually
them
here.
away and repeat the results to better spring.
So
before
basically
any
you end up
force
with
is
a bunch of
applied.
numbers for, you know, the amount of stretch and the amount of force. This column here and this column here is really what you need, right? So if you have a bunch of forces for stretches, then you can graph that. And if you graph it, and you get, I don't know if they show the graph or not. I'll show my version. Yeah, there you go. So they graph it, and you see it's a nice straight line. You're like, ooh, sweet, that's an easy equation. And then you have over here the idea of like once it sort of tapers off and doesn't follow that straight pattern anymore, then you're like, ooh, that's reached, that you've gone past the elastic limit. So what happens is things just start to stretch without the force increasing. So if you're stretching, it's hard to see this with it's hard to really do it by experiment. But if you're stretching an elastic band, you're supposed to sort of notice like force getting more and more and more. And then once you reach the elastic limit, you stretch it another centimeter and the force doesn't change as much. You stretch another centimeter and the force doesn't change as much. And you're just kind of just deforming the material at that point and actually destroying the material at that point, and eventually it just snaps. But I think a lot of people would think that the force just gets bigger and bigger and bigger until it snaps. But there's actually a portion at the end where it kind of starts to stretch without increasing the force. In mechanic land of like working on Jeeps and things, I definitely experience this. If you over torque a bolt, you're tightening up a bolt and you go too far, you get to the point where you turn the wrench another 30 degrees or something, and it doesn't get harder to turn. If you do that, you have stretched the bolt. You've gone past the elastic limit of the bolt, right? So normally stretch another, turn another 30 degrees, it gets a certain amount harder, and it's like pretty obvious. Like it's like harder when you get to that point. But if you go past that elastic limit, it kind of doesn't get harder. And shortly after that, if you keep going, of course, the bolt just snaps right off. So if you've ever experienced that, you start to get that's why mechanics and people that do this a lot sort of get the feel for tightness, because you can kind of just get to the point where you can tell, like, if I go any farther, it's probably going to start to turn without increasing the force as much. So there's that graph. There's the, going past the elastic limit idea. You notice that it's a nice direct relationship. We know that the slope is the same the whole time. The math version is like slope equals, the force over the distance. So you get this like, slope of line business, right? So the idea of being proportional, like I've already written. That slope, of course, like I said on the other page, is your constant proportionality. It's that physical property, right? The physical characteristic of the situation. I've said this multiple times with you guys have analyzed things. Constants of proportionality are always something about the physical characteristics of the situation you're looking at. So in this case, it's the stiffness of the spring, right? When we've seen this in other examples, we looked at like how much acceleration there is for a given force. The proportionality constant was the mass, like a physical characteristic. Voltage equals current times resistance. The resistance of the material is that physical property, right? Even FF equals mu Fn, we've looked at coefficients of friction. These are all simple 3-variable equations where we have one thing depends on another thing. One concept depends on another. Force depends on, or acceleration depends on force. Current depends on voltage, right? Friction depends on the normal force, all those things. So it should be pretty straightforward to understand where the heck F equals kx comes from, and just have a good understanding of it. Warning, when we're looking at the F, I find in the notes or in the solutions for the homework, I wish there was a subscript here like Fs maybe for force of the spring. I find myself writing force of the spring in the net force diagram and net force listings. And the same thing for this one. What do we call it? Elastic potential energy. We call it EE because that's what we used for electric potential energy. So luckily we're not talking about both simultaneously, I guess. We can deal with it, but it bothers me a little bit for sure. But it's commonly shown as EE. Okay, so we are transferring from just talking about forces into talking about energy. Okay, so obviously we can store energy in a spring if it rebounds back to its original shape. We can store energy in it. So we'd have like F equals kx, of course, that force, right? And we know the work done is the energy that would be stored. So work done by a force. Work done equals force times displacement, right? So we know the stored energy would be the work, which would be the force times that displacement. So the force is kx, right? So we're going to get to that in a second. But yeah, that's the change. That's the stored energy. I'm putting there another note about how, like, if this is a change in elastic potential energy and we're changing relative to 0, we don't really need the delta, do we? We're just going to say EE equals, but that's the same as saying delta EE in comparison to 0. So yeah, we're storing energy, releases it back out. Oh, if there's friction, I don't know why I'm mentioning this one exactly right now, but if the amount of energy you'd get out would be less than, like you're not going to get the same amount, right? Out in is, I think they have that backwards there. So you'd have some friction in some situations, but lots of times we're told it's frictionless, which makes it easier, of course. This has to be the other way around. And I want somewhere around here, I have the symbols. There we go. I want the other one. I could just flip it, but why am I not seeing? Just regular. Oh, I guess I have to choose to use the keyboard. That's why. Somewhere around here. There we go. Keyboard is plugged in. So the energy you put in would be greater than the energy you get out if there was friction in the system, is what I was going for there, but had the inequality the wrong way. So similar analysis, where we're talking about work done, force times displacement, area under a force displacement graph. If we had a constant force, then we'd have the area underneath it. In this case, it's not a constant force, but luckily, at least in this case, not like in the gravity case, at least we have uniform change, right? So it's not curving. We have this like linear relationship. This is the F equals kx line here, right? So let me go red here along here. So we have F equals kx, as we previously discussed. Close enough, right? That's why it's this linear line. So of course we're talking about the area under that graph is just a triangle. So the benefits that we continue to reap the rewards of having worked hard on that uniform acceleration stuff in grade 11, because we're just, the idea of the area under the curve should be just obvious and automatic to us here, that it's a triangle, 1/2 base times height, piece of cake, right? So technically we could say 1/2 of delta x and delta f, but again, if we're talking about changes from 0, the deltas are really just the values, so we can get away with just saying x and f, and then we are using right here to there that f equals kx. So we end up with 1/2 of x times kx, which gives us a nice easy formula, 1/2 kx squared, which is very nicely similar to the kinetic energy equation. Okay, so I'll come back to that page in a second. I'm just going to jump right to pasting it on here. So this is that. Let me get a little bit better here. There we go. So this is elastic potential energy, EE. I guess I could put this above as a heading. And then the variables are labeled. All right. So like I said, I'll go back to this page though, in case anybody wants to finish jotting anything down from there. Do we need the full page? Using new equation for us to recognize that we need to use in certain situations. If you're talking about storing energy in a spring, 1/2 kx squared is your friend. Plug numbers in, gives you answers. Okay, anybody need that page some more? Looks like
just in it more, please.
Little bit.
Sorry.
Yep, no worries. Let me know when you're done. Must be a pain on that side, having to like try and key your mic quick. I wish we could just leave mics on and it wasn't.
I'm good now. Thank you.
Yeah, you're welcome. Quick draw on the trigger though, that's good. All right, so a spring with a force constant of 2 newtons per meter is compressed 0.3 meters. Determine the elastic potential energy stored. Determine the force needed to cause that compression. I almost think like we could have that part B gets answered first, since we already, we did that stuff first, but it doesn't matter. Of course, you can do either independently. So we'll get to the units in the end there, I guess, but we can look at them as well. But we're looking for elastic potential energy stored. Of course, we're looking at saying, oh, we're given this information, given the K value, the X, and asked for EE. So you look at your handy dandy equation sheet and remember, oh yeah, I understand this formula to do with elastic potential energy that's stored. And I plug numbers in and I get an answer. And the same thing for the force, right? You would say, oh, I know a force, Kf is Kx equation. And plug numbers in. So this is the first level of kind of questions where it's just like, plug in numbers, get answers. Okay. If we wanted to talk about the units a little more, we could. Like we have F equals Kx. And so if we solve for K, of course, we'd have, F over X, which is newtons per meter. So when they say, oh, the K constant is newtons per meter, then that should make sense, right? That it's newtons per meter. If we had F equals Kx in terms of kilograms, meters, and seconds, it would be kilograms meters per second squared for the mass times the acceleration. And then the K value, when we divide out the M, we can actually list it as, I don't think you'll see it very often, but the K value technically in terms of SI units is kilograms per second squared. Not that it matters, but all the questions I've seen recently, I'll just say newtons per meter. And that's probably enough time for that one. Let me know if you want to go back.
I think I need a bit more time, thanks.
Say you want a bit more? Okay, sure.
Okay, I'm good now, thanks.
All right, stuff. All right, so this one here is a little more tricky. Let's see here. So we got what speed? Yeah, what speed did a 2.5 kilogram block have if it compressed a spring? Let's put another block in the way here so we can just focus on things. If it compressed a spring with a certain spring constant, 0.1 meter as it came to rest. And no friction, thank goodness, because of course that changes things a lot and makes it more complicated. But the idea, of course, is it compressed by 0.1 of a meter as it came to rest. And so the ideas that should be in your head right away is that the kinetic energy it had became elastic potential energy, right? So it's an energy concept question. We know, of course, they're constant and so on, but yeah, we know the initial energy becomes that final energy. The kinetic energy it had becomes the elastic potential energy, right? I kind of prefer the red version personally, but of course you could talk about based on conservation of energy. The initial energy is the same as the final energy. Initial energy was all kinetic, final energy is all elastic, right? So basically, I'm gonna get rid of the please make sure to, but you're gonna communicate. Well, actually, that it refers this refers to either of those. You can do this either way, right? So let's make this purple so that I can match it up with the or here. Like or in purple. Like you can do it either way. I think technically the better way is the black one there, but I like I said, this is so much more obvious, right? That this becomes this, and so they're the same. Anyways, either way you communicate it, you've got the kinetic energy equals the elastic potential energy. So we pull out that kinetic energy formula that we reviewed recently, 1/2 mv squared, and set it equal to 1/2 kx squared. Okay. So I have check marks on there saying like, yep, we know the mass, and yep, we know the k value, and yep, we know the compression. So the only thing we're missing in that combined equation is the speed. So you just have to solve for it. So this is a type 2 kind of question where it wasn't just plug in numbers to one of the new equations. It was instead you had to sort of think your way through it. So plug numbers in, do some algebra, through the magic of mathematics, get an answer of 1.2 meters per second. Technically, the answer is like plus or minus because of the whole plus or minus root thing here, right? I should have a plus or minus if I'm going to talk about it. I should have the plus or minus here also, because technically a positive or a negative 1.2, if you square it, you get a 1.44. So both of those are valid answers. So in the end, you're like, oh, well, obviously the velocity must have been coming in at 1.2. It's not actually that meaningful in this case, but depends on what you defined as positive, I guess. Couldn't have been going away from the spring and never touching it.
So are we assuming that the velocity is constant here, or does it not really matter?
The velocity would be constant up until the time it hits the spring, if that's what you mean. And the reason we can say that is because friction was negligible, right? So while it's slowing down, of course, it's not constant because it's going to start with a velocity of 1.2. If I can ungroup this and grab just the block in a second here. Here we go. Hopefully it's all one piece now. Yeah. So as this thing's coming in, it's coming into the velocity of 1.2, and then it's going to hit the spring, and it's going to go like it's going to spring like when I say screech to a stop, if you will, but it'll certainly come to a stop as the spring compresses. So yeah.
Mr. Warren, I'm kind of confused why the kinetic energy is the same as the elastic potential energy.
Because you started with kinetic energy, right? And that kinetic energy, so you're coming in hot, right? With kinetic energy, and then once it hits the spring, all that kinetic energy changes to be energy stored in the spring. And then the spring would then push it back out, and it would go off with that kinetic energy again. So you have to think as you're coming in to the situation, you've got all of your energies. So you've got kinetic energy, but you don't have any elastic potential energy because you're not touching a spring. And then in the final case, all of your kinetic energy is gone, of course, right? 0. And then you end up with, basically the best way to answer your question is to rigorously talk about this whole conservation of energy idea, right? And so the idea is that your energy in the first place has to, the initial energy has to equal the final energy. That's just the concept of energy is conserved in systems. So if you had kinetic energy to start out with and no elastic, and then in the end you don't have any kinetic, it must have become the elastic. And you can visualize it here. Coming in with kinetic energy, compresses the spring, now it's got elastic potential energy stored in the spring, like that, right? Does that help justify that for you?
Yeah, that makes more sense. Thank you.
Yeah, no problem. So then that's why we're able to make this statement here. And that's a good question for you to ask, okay? Because we definitely have to be okay with the idea that there's some thought process here that I'm circling with the mouse here that leads to this statement. And that's critical, of course, because then we're able to calculate the speed that it must have had.
So is the speed going in the same as the speed coming out?
Yes. Yep. If there's no friction, yes. In reality, no. Because in reality, you'd actually have some friction along here, and so you'd lose some speed as you're sliding along that surface, and then you'd lose some speed as you're sliding here, and you'd lose some speed as you're sliding out, and you'd lose, so if you're losing speed all the time, of course not, they wouldn't be the same. Plus also, there's also some internal friction, they call it. So I was visualizing the actual friction between the block and the surface, right? But even if this was a rigid spring, just attached to a wall, let's get rid of the floor. This could be a spring that's attached to a wall, right? So there isn't actually any friction grinding against the floor even. Even then, it's obviously like you've probably played with springs at some point in your life. If you push this thing in here and make it go springing back and forth, is it going to spring back and forth forever? Of course not. And that's because there's actually some internal friction as well within like the molecules of the spring itself. So if you did spring it in as it pushes out, you'd actually lose some energy within the spring itself, and so it would also be slower for that reason as well. So saying friction is negligible here is a big statement for sure. So what you could do, if your next question would be like, well, what if there was friction? What you do is you basically test and you look at, say you send it in with 1.2 meters per second and you see what it comes out with. And if you see that it comes out with, say, only 1 meter per second, you'd be like, oh, it lost 0.2 meters per second, right? So then you'd have, energy lost due to friction. So you'd say, oh, well, I had 1.2. That corresponds to, I'll just circle with the mouse here, this much energy. This much energy here, sorry. Is that right? Yeah, well, if you plug that number in, you'd say, oh, how much energy do they have? And then in the end, I only had 1, so you do a 1/2 mass times 1 squared. And then the difference between those would identify the amount of energy you actually lost to friction. Okay, and you could say, oh, that was because of the rubbing on the surface, and because of the spring, or if it was, like I said, if it was just attached to a wall and there wasn't a floor to rub against, then you could say, oh, that energy was lost internally within the spring. What does that become? Well, it becomes heat, of course, right? So have you ever taken a piece of metal and bent it back and forth a bunch of times and made it get really hot? That's what happens in springs, just way less hot, right? They bounce back and forth and some of the energy just ends up as heat and dissipates into the room and no one notices it. But it did happen. Questions? Good questions, by the way. Any more? All right. So the questions to do with Hooke's law and elastic potential energy are there, and they're all worked out and will be posted as well. So it feels really weird. We're done like an hour early, but I've given you enough new material that you need to have some time to practice it. So I'll stick around right near here until noon. And if you have any questions, you can just ask right away and get answers right away. So I highly recommend you start working on these questions while I'm key of the mic away, rather than having to wait for emails and so on. Okay. But whatever you do, it's up to you. Yeah, so I'm just going to turn my mic off and might as well not share the screen for a bit while I'm uploading all these files, so you don't have to hear the clicking and so on. But I am right here to answer questions. Just a quick little attendance check here. Oh, Margot again. Is that right? Goodness. And Dawson, of course. All right. Stop recording.